Hello, everybody. Let's talk about some OChem. So today we're going to talk about the alkane functional group, and we're going to cover some of their properties and characteristics. Okay, so take a look at your key concepts. We're in Unit 1, Part 2. You can find a copy of that on Canvas. So alkanes are the simplest functional group. Consists of simply, where's my mouse? Of a carbon-carbon single bond. That's a fundamental property of an alkane, just a carbon-carbon single bond. Okay, molecules that consist only of carbon-carbon single bonds and hydrogens, well, they can go by various names. They can be called aliphatic compounds. Aliphatic, I believe, comes from a Greek word meaning fat, and we're talking about these kind of fats, right? Trans fats, saturated fats. So those molecules that make up the fats in our diet, a big portion of the molecule is simply a chain of carbons, singly bonded together and attached to hydrogen. Not the entire molecule, but a large portion of the molecule. Okay, so that's the origin of aliphatic. You can also call the entire molecule with C's and H's singly bonded. Just the whole molecule could be an alkane. You can also call them saturated hydrocarbons, right? Hydrocarbons is a good name. Molecules with just hydrogen and carbon. And if they're saturated, then these molecules contain the maximum number of hydrogen atoms. So if you think of an alkene, a carbon-carbon double bond, ooh, okay, that's not an alkane. An alkene has a double bond in it, and it will also have fewer hydrogens than the corresponding alkane. Okay, it turns out because carbon bonds 4 times and hydrogen only once, if it's saturated, maxed out on hydrogen, a saturated hydrocarbon must have a chemical formula that matches this pattern. So essentially what you do, it's a nice shortcut. So if I want to know what the chemical formula is for octane, right? So how many carbons are there? There's 8. We'll get into naming molecules in just a minute. Fun. But for now, octane is a molecule with 8 carbons. And then what you could do to predict how many hydrogens is drawing out all 8 carbons, putting 4 bonds on all those carbon atoms, attaching hydrogens, and then adding them up. Okay, that's going to take some time. It's better just remember that you double the number of carbons and add 2 more. Double the number of carbons, 2 times 8 is 16, and then add 2 more, that's 18. And if you want to draw out octane, you can check that, or you can Google it. Okay, so it is a good idea to memorize that. Turns out we're going to use this formula later in the course for another purpose. So a couple reasons why you should memorize it. What are some of the characteristic traits of alkanes? Well, they don't always have to be a straight line of carbons, but they can be. So down here, we have alkanes that are following one another in a sequential fashion. So this type of alkane can be called a straight chain alkane. It can also be called unbranched, makes sense. An old way of labeling these types of molecules is put a little N, which stands for normal, the normal arrangement of carbon, I guess, one after another. Those are N-alkanes. Okay, and then just a fine point here. This is a complete structural formula. What if we change to a skeletal drawing, right? So how many carbons are here? It's 5. So let's draw the skeletal drawing for this molecule pentane. Well, one option is to do it this way, right? That is 6. Let's not do 6. Let's do 5. 1, 2, 3, 4, 5. Or you could have done it like a letter W. Or you could have done it that way. Yeah, that's probably not your preferred drawing, but 1 carbon, 2, 3, 4, 5. That is still a normal straight chain alkane. I know it's not as straight as this arrangement, but it's still the same molecule. 5 carbons falling one after the other. So just be aware that skeletal drawings can be bent or curved. And we have to think a little bit and ask ourselves, well, wait, what does this represent? It's the same molecule here, which turns out to be pentane or N-pentane. How many carbons are here? Sorry, how many hydrogens are here? First ask how many carbons? What's the chemical formula? Maybe a better question. Well, there's 5 carbons, right? So you could count them. That ain't too hard. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 12, but the faster way is just to use the formula, right? 2 times 5 is 10, plus 2 more is 12. That's a lot faster. Okay, second class of alkanes are branched alkanes. Here we can take the same molecule and make an isomer of it. Remember from the last video, isomers are molecules that are different but possess the same chemical formula. So it turns out there's 1, 2, 3, 4, 5 carbons here. And there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 again. Hey, that's the same formula. But this is not a straight chain. It's 4 in a row with a branch coming off of the, well, I would say the third carbon from reading it from left to right. But you could also say it's the second carbon if you read it from right side to left. We'll look in that later. But anyways, there's a branching carbon here. This is a branched alkane. It's an isomer of pentane, and that's one of the common names for the molecule, isopentane. Okay, you don't have to memorize isopentane. We can also take 5 carbons and tie them end to end. Skeleton drawing might look like something like that. And so you'd say, hey, every carbon possesses 2 hydrogens. Wait a second, 2 times 5 is 10. This is not saturated. It does not have the maximum number of hydrogens for 5 carbons. 5 carbons can hold up to 12 hydrogens. Okay, on the other hand, what's the functional group in this molecule? Only alkanes. There's 5 carbon-carbon single bonds. So it is an alkane, it's just not saturated. It's a hydrocarbon, but not saturated. Oh, we can call them ring compounds or cyclic compounds. Scientists love labels. Some other important properties of alkanes. This is going to build off of general chemistry. So we can predict, or at least see trends. You can't predict the actual value, but you can predict trends in boiling points and melting points. So this is a popular question on the MCAT, the medical admissions test, medical college admission test, MCAT, and as well as dental admission tests. This is a minor topic, and so a lot of students don't focus on this. Yikes. Yeah, MCAT's a tough exam. So it's heads up there. So what do you need to know for the MCAT? What do you need to know for my test? You need to know the trend. And it begins by reviewing your intermolecular forces, right? So there's hydrogen bonding, dipole, and van der Waals or London dispersion forces. And it depends on the type of molecule as to which intermolecular force dominates, right? So hydrogen bonding, you gotta have that OH or NH or FH bond in it. Dipole, the molecules have to be polar, meaning that there are atoms present that are more electronegative than the other atoms. And then finally, if you don't have any of that, it's completely nonpolar, then you have the weakest force, London dispersion and van der Waals forces. It goes by 2 names. Either name works for my class. So if you have an alkane, got a sentence here, the alkane, if a molecule only contains an alkane functional group, it must be nonpolar. I got the question, why? You really need to know your definitions. So what's an alkane? Carbon-carbon. And then that's kind of incomplete, right? So if a molecule only contains carbon-carbon, you're not going to get 4 bonds that way unless you make a cyclic, and then you can't get saturated hydrocarbons. The other thing that's implied is that an alkane usually has hydrogen too. So carbon-carbon single bonds and hydrogen make up the alkane functional group. And that's it. If the molecule only has alkanes present, like this one does, you only have CC and CH bonds, single bonds. And carbon and hydrogen are about equally electronegative. It's a non-polar covalent bond. And of course, between a carbon and carbon, that's a non-polar covalent bond too. Yeah, all these bonds are non-polar. Neither carbon nor hydrogen has a significantly greater electronegativity than the other. Yeah, it's a nonpolar molecule because it's made of nonpolar covalent bonds. So the London dispersion force operates here. I like to think of it as Velcro. It's not Velcro, but it helps. If you recognize that the molecule possesses only London dispersion forces to hold one molecule to another molecule, then you can make some predictions. And it's helpful to think of it as Velcro, right? So 2 things you need to know. The melting point and boiling points are going to increase with molar mass, molecular weight. Why? Think about Velcro. So if I have pentane, again, 5 carbons, and I got a bunch of pentane molecules in a beaker, it's a liquid, turns out, they stick together and stay in the liquid phase through van der Waals or London dispersion forces. And so I'm thinking, well, how does this molecule evaporate? It needs to unstick from its neighbor. So if you got a piece of one side's Velcro and the other side's Velcro and it sticks together, you have to peel it apart to get it to separate. Okay, but if you make the molecule bigger, then you have a longer strip of Velcro. And I should have made them line up a little bit better. I'm a little sloppy here. But now think about a longer sheet of Velcro and you have to peel it completely apart. That's going to take more energy, take more work. And it's also going to take more heat energy to make them boil. So that's something to remember. Maybe if you're going to take the MCAT, it might show up. The temperature which you need to heat something to melt it or to boil it is going to increase if the molecule is also increasing. And then we get the reverse thing. Chemistry's full of opposites. If you start increasing the branching, so let's stay with 5 carbons and go to its isomer, or one of the isomers. Yeah, I got 5 carbons there. Now let's get this molecule that has a branch. I got 4 in a row, and then I have a carbon that branches off. And now think of Velcro in a sense. Like this is a Velcro end and it's trying to stick to this part of the molecule. That's not much overlap. It's not stuck together very well at all. So it's easy to separate it, which means you don't have to heat it as much to make these molecules separate and jump into the gas phase. Or if it's a solid, you give a little thermal energy, vibrates a little bit as you heat it up, and they can unstick pretty well and melt. Okay, so as you bring in more branches, that's going to lower the melting point or the boiling point. 2 important trends to keep note of. We're going to keep coming back to this idea as we go through the whole year of organic chemistry. Okay, what else do we need to know about alkanes? They are very stable. The carbon-carbon single bond is a very strong, stable bond. That is good for us. It means there's not a whole bunch of reactions that you have to memorize. Okay. So there's very few reactions. The other thing too is if you got a brand new molecule and I ask you, hey, predict the product of this reaction, as you inspect the molecule, you'll look for functional groups and you'll get in the habit of, oh, here's a carbon-carbon single bond. Oh, here's another carbon-carbon single bond. You probably can ignore it. It's probably not going to change because they're so stable, the reaction won't happen at the carbon-carbon single bond. It's likely true that the carbon-hydrogen bond won't react either. Now, there's going to be exceptions to that. I got one down below. But as a rule of thumb, as a little guideline to help us get through this course, yeah, alkanes pretty much are not going to react. Other functional groups are more reactive, and they're the ones we'll look out for. Cool. Okay, so one of the important reactions, you may already know it, is combustion. Yeah, let's burn these alkanes. We do in the the engines of our car every day. We burn gasoline, or we light up a Bunsen burner, or maybe have a gas stove at home. That's a combustion reaction. Kind of important. It makes our world go. And so here's actually the combustion reaction for a Bunsen burner. Natural gas is essentially not 100% pure, but largely methane, CH4, in the gas phase. Mix in 2 molecules of oxygen, we're going to balance it, and you form 1 molecule of carbon dioxide, 2 molecules of water. Okay. When I say memorize it, you could measure it to this level of detail. That's the general chemistry way we used to do reactions. The organic chemist comes along and says, wait, organic chemistry is the study of carbon. I'm focusing on the letter C in my reactions. Where is carbon? Well, carbon's right here as methane. This molecule is oxygen, kind of important. Yeah, it's required for the reaction, but this is organic chemistry. O2 doesn't have any carbon, so it's less important from the point of view of organic chemists. So what we traditionally do is we rewrite the reaction to focus on the carbon. So put the oxygen gas over the arrow, meaning, hey, let's look at the first organic molecule and see what it changes into. How did it change? When it interacted with oxygen gas. So this is the combustion reaction written out again. You'll notice that we sometimes leave off side reactions. Side products, rather. This first reaction is 100% full credit on my exams, but where's the water? Yeah, so some students like to put it in there. And that's just extra data. The organic chemist says, where's the letter C in this molecule? There's no carbon in water. It's not organic. I really don't care. So that's a nice shortcut. The other cool shortcut is the organic chemist usually doesn't balance their equations. We're too focused on carbon and all the cool things it can do. So we don't have time to be balancing numbers. Well, that's a bit of an exaggeration. If you do go in the lab, you need to balance your equations so you measure things out correctly. But it's a nice shortcut that you get to exploit on exams. So let's go back up to here, the general chemistry way of writing 2 molecules of C6H14 with 19 molecules of oxygen gas, makes 12 molecules of carbon dioxide and 14 molecules of water. Lots of detail there. All the physical states are shown. Everybody's a gas. Okay, organic chemist says, tell me about carbon. So C6H14, one way to draw it is 6 in a row. Maybe it's a straight chain alkane. And if so, okay, here's the reaction for C6H14 as a straight chain to react with oxygen to form carbon dioxide. And I'm not balancing. It's the same overall reaction as above. Whether it's CH4 or this molecule with 6 carbons, the product's the same, just CO2. Much less to memorize. So run with that. What else do I have here? Oh, I made a critical assumption and a bad one. You can't use this chemical formula to predict the structure, right? C6H4 has isomers. So here's one other isomer. This might be the reaction. There's 6 carbons here. And if you break this down and map out all the hydrogens, you'll also count 14 hydrogens. This is a branched alkane. It's also saturated. It's C6H14. What's kind of cool though is whether you have this isomer or this isomer, the products are the same. It just goes to CO2 when you burn it in the presence of this reagent, O2. Okay, nice shortcut. So we're going to get used to drawing our reactions this way. And in lab reports, we're going to go back to the old Gen Chem fashion when we have to balance our equations and calculate the limiting reagent, calculate the percent yield. Yeah, you'll do that in the lab. But on the exams, we're focusing on carbon. We're going to take this shortcut method of writing a chemical reaction. Okay, that column of data is done. Oh boy, what does that say? Memorize, yeah, okay, so more to memorize. One of the things we're going to do in this class is learn how to name organic molecules. We're going to name them. And we're going to begin with the alkane functional group. And as we work through the entire year of organic chemistry, we'll look at new functional groups and learn how to name those molecules possessing those functional groups. Okay, so let's look at what we have to memorize. The molecule has one carbon, and that's it. And it's a alkane, which means it only has C's and H's and single bonds. It only has one carbon. There's only one possible formula, CH4, that's methane. Two carbons, ethane. Here's the chemical formula, but do we have to memorize that? No, memorize this. Memorize the formula. So one carbon is methane, two carbons is ethane, three carbons is propane, four carbons is butane. These are weird names. Five carbons is pentane. Wait, I've heard of the pentagon. Pentagon is something with five sides. Ooh, pentane sounds like pentagon. It's five sides. Yay. So go over the math department, review your polygons. The hexagon, six-sided polygon. So yeah, hexane is six sides. In the Olympics, there's an event the women perform where they have to do 7 events, 7 tasks. That's a heptathlon. Yeah, 7 events, 7 carbons in heptane. An octopus has 8 arms, so octane's a good name for the molecule with 8 carbons. Nonane sounds like 9. We got nothing for that. Nonane is 9 carbons. Decane, 10 years is a decade. The Dewey Decimal System has, it's a base 10 numbering system. Decade means 10. It's the methane, ethane, propane that's the most troublesome. And a few years ago, students got the greatest ideas. They said, just remember Molly eats peanut butter. Or maybe Mike eats peanut butter. Mabel eats, let's do Mabel. Mabel eats peanut butter. And then you got the first letter of the first 4 alkane names. M for methane, E for ethane, P for propane, and yes, that's the same gas you use on your gas barbecue grill, propane, and B for butane. Ooh, so you even get the BUT part for butane. That's a bonus. Molly eats peanut butter. Mabel. Maple and Dipper. Gravity Falls. Yay. Had some students, I forget who told me this. They said, gosh, organic chemistry, it's just a memorization marathon. Don't sprint and cram. It's a long race. Pace yourself. So true. That's good advice. Okay. Next item on our agenda. I think this is the last one. Classifying. For you? Yes. Okay. Last thing we want to do is just introduce this tool called classifying atoms, and we'll first talk about classifying carbon. Okay. It turns out that we have oversimplified things. We said that a carbon-carbon single bond is an alkane. Still true, but not all carbon-carbon single bonds are the same. So there are times, and then more specifically, part of the alkane functional group are the attached hydrogens, right? So if you look down here, this bond in red is part of the alkane functional group, connects a carbon to a carbon. But technically speaking, the H's are part of the alkane functional group too. But if you do some careful reaction studies, you'll discover that in certain reactions, sometimes these hydrogens at the end of the chain are more reactive than the hydrogens in the middle. And if you change your reagents, in those cases, sometimes the hydrogens in the middle are more reactive than the hydrogens on the end. And so what gives? Well, they're different from each other. They're slightly different. Nature, she makes all the rules. It's up to us to try and figure them out. And so what scientists have done is they said, you know what? To get a handle on this different reactivity, let's label the carbons, and then we can label the hydrogens too. And that'll help us just kind of put a handle on these differences in reactivity. So I need you to be able to classify carbon. Okay, so how do you do that? Here's a 4-step method. Step 1, find your carbon you want to classify. Choose one. Step 2, well, carbon honk says HONC 1, 2, 3, 4. Carbon's supposed to bond 4 times, so go find them. Find the 4 bonds to that carbon atom. And now, just for those 4 bonds, look at the end of the bond. What atom is attached to that carbon through its 4 bonds? And whatever you count will give you the classification. So let's try it out. Let's classify this carbon down here. Let's put a little arrow there. So I want to classify this carbon and not look at the answer. Whoops, everyone just did. Okay, the process is, hey, I chose my carbon. That was step 1. Where are the 4 bonds? 3 of the bonds are to each of the hydrogens. The 4th bond is to this carbon on the right. Okay, so for this carbon, how many of those 4 bonds attach a carbon atom? Just 1. Yeah, so if it has 1 attached atom, we say it's a 1 degree, 1st degree, or a primary carbon. That's a lot of letters to write out. So maybe on an exam, if I ask you to classify, you would say, okay, this carbon is 1st degree. I'll say, yep, that's correct. And the process just continues from there. So now if we want to classify this other carbon, find the 4 bonds. Here's 1, go to H. Here's 1 to carbon. Ooh, that counts, that's 1 carbon. Here's a bond, that's H. Skip it. Here's the 4th bond to that carbon. It's connected to another carbon. We've got 2 carbons. That makes it secondary. This is a secondary carbon, a degree 2 carbon. Let's just keep going, just to make sure we're clear. This carbon here, if you go up, there's an O, and you stop there. Don't keep looking and see this carbon in the distance. This carbon is connected to oxygen, not to this carbon that we're trying to classify, right? It's connected directly to an O. Skip it, it's not a C. Ooh, here's a C on the right. Here's a C down below, and who cares if there's fluorine there? Don't let that distract you. What is at the end of this bond? A C. And over here on the left side, there's another C. There's 3 of them. Yeah, that makes it a tertiary, a degree 3, a 3rd degree carbon. And we're done. You look at this carbon, there's 4 attached carbons. That's quaternary carbon, or a 4th degree. Yay, as simple as that. So just get comfortable with that. Once you're comfortable classifying carbon, then you can move on to classify other atoms. Be careful, the rules change a little bit. Okay, so when you're trying to classify other atoms, like a hydrogen, we'll have to do that. We're also going to have to classify functional groups. You use the process for classifying carbon. Well, let's walk through the whole thing. Now let's summarize. That's a better idea. When you're classifying hydrogen and functional groups, first classify the attached carbon, and then simply share the label with these functional groups in hydrogen. If that wasn't clear, let's try it out. Step 1 for classifying hydrogen, go find one. Okay, I'm gonna pick this one. One of those 3. What do? Classify the attached carbon. How'd you do that? Find carbon, just did it. How many bonds? 4 bonds. Where are they attached? For this carbon, 3 of the bonds are to H, skip them. The 4th one's connected to this carbon over here, that's 1. So this carbon is a 1st degree carbon, a primary carbon. What do you do with that? You use the same classification. These hydrogens are also primary hydrogens. What about if we want to classify one of the hydrogens attached to this carbon? Well, then you're probably gonna have to draw it in. This is skeletal drawing. Every bend represents a C. There's 1 bond to the left, 1 bond to the right. That's 2 of the 4 bonds. So I gotta add a 3rd bond with an H, and a 4th bond with an H to get out of skeletal drawing. Let's classify this hydrogen. I'll go back and classify the carbon. Okay, carbon, what's your classification? I think of carbon as being a person with 4 arms Helps me. More of a visual learner. It's got 4 arms. Okay, who are you holding hands with, carbon? Carbon says, okay, on my left, I got another carbon over here. On my right, I got oxygen. Okay, don't count that one. Down below to my left, on my 3rd arm, I'm holding on to a hydrogen. Don't count that one. And over here on your right, bottom right, there's not a hydrogen. Okay, so out of the 4 bonds, only one of them is attached to a carbon. This is also a primary carbon. There's only one attached carbon. So what degree is this hydrogen? Primary as well. So whatever the label is for the attached carbon, that's shared with the hydrogen. And we follow the same pattern for the alcohol group or any other functional group, except for nitrogen. Okay, nitrogen, you count it like carbon. We'll do that later next semester. So if I ask you to classify functional groups, I will not give you any that possess nitrogen. So the other functional groups, like an alcohol group, OH group, that's an alcohol group. Hey, oxygen or no alcohol group, what's your classification? Well, go find its attached carbon and classify that. Okay, carbon, where are your 4 arms, 4 bonds? Well, one's to the oxygen, skip it. One's to hydrogen, skip that. One is to this carbon down here, count that one. And one's to the carbon on the right, 2. That's it. This is a secondary carbon, making this a secondary alcohol. Cool? Okay, that's all for now. See you next time.